there, then
I got my PhD in Bath.
oh, okay, PhD in Bath.
With some prominent supervisors, by the way.
We were both present.
Okay, with some prominent
Two
supervisors.
prominent supervisors.
Yes,
Yeah.
and then you move to Cardiff, then Montpellier, and then you will start in Bath in.
I went to Montpellier after Cardiff. Then
Marseille,
Montpellier, yeah.
Montpellier, and now.
Yeah, I've been everywhere.
Okay.
By the way,
Quantum particle.
for this reason, you listed Bath, Cardiff, Montpellier, Marseille. Now back to Bath. He is listed as, his affiliation is listed as Bristol.
Yeah.
Yes. Okay, okay, but.
Simulator. Close enough.
Okay, too complicated, but you will be in Bath
In 3 weeks.
in 3 weeks. Yeah. Okay.
So then
Great.
I can change this long title to Bath.
Yeah, and I think we have quite a prominent group of people doing homogenization for periodic operators here, and I think you are. Am I right that you are the first to speak? You haven't. I mean, we didn't have homogenization talks at this program so far. I mean, we will have lots of them further on, but you will have the honor of opening the homogenization series at the program.
Well, if it's bad this time, it'll get better next time. That's a good thing. So, so my talk today will be on resolvent estimates for high contrast elliptic problems with periodic coefficients. But I'm going to split my talk into 2 parts, actually. The first part will be about the homogenization theory. But because before I introduce the results and the advances me and Kyria have made on these problems, we first have to understand what the difficulty is with attaining resolvent estimates for these problems. And I will describe this difficulty in the context of homogenization theory. And I will also present the state-of-the-art results, if you will, of these problems via homogenization theory. And then develop on these ideas and show you in the second part mine and Kyria's contribution to this problem. Well, these types of problems in general. Okay. So, well, there's no potential in my problems. The periodicity in these problems are inside the coefficients. So I'll be studying second-order elliptic problems of this form, divergence-type equations with coefficients that are periodic, and the periodicity is small. And for this small parameter, we call it epsilon. But there's an additional complication or interest, if you will. These coefficients also depend on the small parameter. And these coefficients depend on the small parameter in the following way. For each fixed periodicity, these coefficients are elliptic, uniformly elliptic. But the ellipticity constant depends on the small parameter. And this ellipticity constant will go to 0 as the small parameter goes to 0.
Sorry, may I ask you something? You said there is no potential. Is it because it's straightforward and trivial to add potential, or is it because when you add potential, it would have to be scaled in different?
It's because I know absolutely nothing about potential problems.
However, I think the former assertion is true.
What, trivial?
This is straightforward. For purposes of homogenization, we simply take the periodic average of the potential.
But what if the potential also isn't just periodic, but it depends on the small parameter, some kind of weight?
In this case, it's a bit
Then
more
it's
subtle,
not
right?
trivial.
That's a bit more subtle.
Yeah.
Yeah.
But you could probably do things for such a case as well with the underlying mechanism. So for the purpose of this talk today, what I'm interested in is we have these operators A epsilon. And what I would like to know is information about the spectrum. And I also would like to know about the spectral projections as well and the eigenfunctions in the spectral subspaces.
Just preliminary question. However, what is the behavior of C1 as epsilon tends to 0?
Well, that will depend.
In principle,
the behavior.
just a few words.
Oh, for example, well, you will see in a couple of slides. Can I say that? So one of the examples of the behavior of C1 will be what I will show in a few slides. But basically,
Power life.
for example, it could be piecewise constant coefficients, where one of the coefficients goes to 0 on a set of non-measure 0.
So this is the central issue, and the speaker is going to make a big fuss on what on the next slide, not you have.
Yeah.
Prevent.
Actually, that is the entire issue. The behavior of C1 will change everything. And if you change the behavior of C1, then you will change everything again.
And why do you have this picture? Because A is compactly supported somewhere, or what
No,
is
A
why-
is
why
again,
is this
uh,
picture?
page
Why
below
is this
that.
picture?
okay, in 2 slides. But no, A is a periodic coefficient, and it will have, and this is the periodic reference cell. So A is periodic with respect to this cell, and this cell is periodically distributed inside the domain. Okay?
Okay.
So I want to study the spectrum. Well, in the first small parameter epsilon, I want to study this asymptotics of this spectrum. In the following sense, there we have a family of sets, and I want to know what the set limit of this family is. But I want to know more than this. I want to know if I can find this set limit and characterize it. I want to know the rate of convergence as well.
So you don't assume coefficients to be continuous at all.
L infinity.
L infinity, that's it.
Yeah, okay, for you guys, I probably should have added a few more assumptions, but I was trying to be as tame as possible with the slides. L infinity coefficients. Right, well, okay, so there is a simple class.
Still,
Uh-huh.
so these circles there, the meaning. They're just meaningless, right?
The meaning, it's, well,
It's an example. It's an example.
they're aesthetically pleasing. I
So
mean,
it's just an example, but in principle it doesn't have any meaning.
It's illustration of periodicity.
Yes. It's an illustration of the underlying
It's not, because you know, usually people do something like that when the
Solid
the
balls.
coefficient outside is a constant or a zero outside the circle.
Shane, am I right that at some point you will have degeneration of electricity, say, on those circles or something like that?
Well,
But why don't we just
on
move
the
on?
on the
Let's just
circles
move
on the circles is boring. You can actually have degeneration of electricity outside of the
Let him
circles.
give his talk, come on.
Yeah.
Just go to the next slide, you'll state all the conditions.
Okay.
I actually won't, but I should have done.
Yeah, you see? So who's right?
We will have some simple examples. Okay, you're right. If you want to be right, I don't mind.
Okay.
Anyway, there are a simple class of problems here. If we have a family of
No,
operators,
it's periodic problem in the space.
Yes, but the boundary of the.
it can be in the bounded domain or in the space. I haven't decided. I'm just. Oh, this is a slide to set the scene for the class of problems I like to study in my research. I will get to the specific examples in a few slides. Okay. So there are a simple subclass of these problems. If we have a family of operators A epsilon whose resolvents converge in a certain sense, then we can immediately determine information about the spectrum. And what I mean is, if we study the resolvent problem here, so we have a term f in some Hilbert space, and we look at the solutions u epsilon to this resolvent problem. And we have another operator called A naught for the same f who has a solution to its resolvent problem. And let's say that both operators are non-negative and self-adjoint. Then we can say that it will norm-resolvent converge if the resolvents converge in norm just for at the point 1 here on the resolvent problem for s equals 1 or whatever. What I mean here is that the difference between the solutions u epsilon and u naught are uniformly bounded in f, and this constant will go to 0 as epsilon goes to 0. For these type of problems, you have straight away the convergence of the spectrum in the following sense. Which means every point of the spectrum of A naught is a limit of sequence from the spectrum of A epsilon. And if you have a converging sequence from the spectrum of sigma A epsilon, it will converge to a point, and this point is in the spectrum of A naught. But this is very simple, and this doesn't work in these degenerate problems that we're studying. And I would like to explain in the next 10 or so or 20 minutes why this is the case. But when does it work? Well, let's look at the classical problem. So we have a problem now, so maybe I can answer a few people's reasons for the pictures. So I have the periodic reference cell, and I choose my coefficients just to be piecewise constant in each cell. So the ellipticity constant is uniform in epsilon. So for these problems in the whole space or in a bounded domain with whatever boundary condition you would like, Neumann-Dirichlet boundary condition, we have a homogenization theory. So let's say we have a right-hand side f in L2 and we are in W120. Oh, by the way, when I say W12, I'll say H1 here. The subgraph space W12 is H13. Or maybe for you too, but I will just say H1. And we know that these solutions strongly converge in L2 to some limit U0. And U0 will satisfy a problem of the same form as the original problem, the key difference being that these coefficients are constant now. So this is classical homogenization theory. And of course this will, what's the relationship between the spectrum? The question is, what's the relationship between the spectrum of A epsilon and the spectrum of A naught? And well, the homogenization theory tells us that they converge in a resolvent sense, but we have more information. We have this very nice result of Berman and Susskind that says actually the difference between the norms is uniformly bounded by, in the norm sense, is bounded by epsilon. And this is the best bound you can get. It's the strictest bound. And what does this mean for the spectrum? Well, in the example of a bounded domain, these operators are just compact because they have compact resolvents. So the spectrum is discrete, and for each k, the eigenvalue of lambda epsilon k minus the eigenvalue of lambda naught k is bounded by epsilon. Now I want some similar types of statements for the more degenerate case where the coefficients aren't uniformly elliptic.
Excuse me. If you have bounded domain, how does it depend, if it does, upon epsilon? How you scale your bounded domain if you want?
If you just put a bounded domain on the big and on the macroscopic picture.
It does
The domain
depend.
is fixed.
You
the
don't
domain is
depend
fixed.
on
The
epsilon.
domain
The
is
domain
fixed.
The periodic
Just
coefficients are
floating.
changing.
The coefficients of the equation change, but the domain is fixed.
Yeah, the
So you put more and more of it.
more and more balls in the limit. They become smaller and smaller and smaller.
And you probably mean plus, not minus identity in the resolvent.
Ah, yeah. Yeah. Well, that would that would be a total massive problem if we would be inside the spectrum. So yeah, for the whole space, yeah, there's a plus here. So let me go to the high contrast problems now. And actually, let's just imagine we're in the, well, I won't say we're in the whole space, we're in a bounded domain. I'm just going to talk about the coefficients because the key is the coefficients. The leading order term, the key is the coefficients. And now we will study the problem where the coefficients are 1 in the matrix phase and epsilon squared inside the inclusion. And
Like this scaling, the period is equal to epsilon, and you have also epsilon square. Why square and first power? Is it?
Well, you
is
can
it
you can write epsilon to
Are
the
there some
alpha,
physical
but
reasons or?
there are physical reasons as well. In the wave propagation problem, the epsilon squared means even if you have a very small frequency in the long wavelength approximation, the wavelength is order 1 inside the ball, so it feels the presence of the small inclusions. But mathematically, this is the interesting case.
Physically, it is often related to the so-called micro-resonant time scaling.
Because the wavelength is small
Instead,
and it feels the inclusion, it feels the resonance.
because of the high contrast, the same frequency generates highly contrasted wavelengths, and you are interested in wavelengths in the inclusion comparable to the size of the inclusion, which is epsilon. It is a resonance scaling, right? But in the matrix, it is still long wavelength, right? It is actually these two assumptions, right? High contrast and resonance scaling in the inclusion leads simple dimension analysis leads to exponent equal to.
Well, you see that it is a quadratic operator,
Yeah.
differentiation, so it scales exactly linearly with x.
Yes.
So we have two, and it's dimension independent. So epsilon squared is for all dimensions.
Yeah.
Yeah,
It's
because
order
the creator
epsilon
of-
squared. You can stick whatever elliptic positive coefficients. Smooth piecewise constant. But I just put 1 because it's for the sake of the talk. It's nice. Well, you will see. I will write the limit equation soon, and it's better to have 1. I went ahead. So anyway, these. If I have a right hand side in L2, now I have a solution in H1. But the gradient of the L2 norm of the gradients inside the balls is now unbounded. It's order epsilon minus 1. And this changes everything. And a good way to see it is to perform some multi-scale asymptotics on this problem. And you see up to leading order that the solution still depends on epsilon. This is the key point. The leading order term for these problems will always depend on epsilon. And this V is a function who's compactly supported to the inclusion.
As I think Jens mentioned, that because of the certain order operator, it's exactly because epsilon squared, right? You have there is no any more reason not dependent main order term on x over epsilon on the periodicity. It's exactly supports in terms of asymptotics this micro-resonant type effect, right? You have microscopic variation, but only in one phase.
I think I might need 2 hours. I don't think I'll get through this talk in 1 hour.
This is what I told you.
So what does this mean if I was to study the convergence in the normal topology on that too? So we have a weak convergence here, and the weak limit is the function u plus the mean value of this function v with respect to the macroscopic variable y. This function is periodic in y. And this averaging, when you want to look at the limits in spectrum, it destroys everything. This just absolutely kills the game. And there's a simple example that shows this. So let's look at the following resolvent problem. I'm just going to set a epsilon to be epsilon squared everywhere now. And I'll look at the Dirichlet problem. So I bounded them in with balls of period epsilon. Well, there's no balls. So I bounded them in and the coefficients are epsilon squared. And I look at the following resolving problem. Well, these functions are bounded in L2 and they weakly converge to some function u0. And u0 just satisfies the following limits equation. So that you're not going to get any information about the spectrum from this. In fact, it says that the resolvent of A epsilon here just weakly converges to 0. So what we do for these sorts of problems in homogenization is we change our notion of convergence. And what we have to do is introduce a notion of convergence which pays attention to the oscillations on the small scale. And you do this by modifying your convergence to include test functions which also oscillate on the small scale. And if nobody is familiar with this, there's always a nice example. There's always a nice example people give with this, and they say that sine of x over epsilon will weakly converge to 0, but sine of x over epsilon will 2-scale converge to sine of y. So the periods of order epsilon are maintained by this notion of convergence. And it's weakly converges to 0 because it weakly converges to its mean value, which is 0 over its periodic reference cell. And with weak, there's always an analogous notion of strong, which says a sequence will strongly 2-scale converge if it weakly 2-scale converges and its L2 norms converge. So now let's look back at this very degenerate problem. So we have the same problem before, but now the solution is strong. But now we have f epsilon, the strongly 2-scale converges to some f. You can just say f epsilon equals f, for example. And the solution is u epsilon now will strongly 2-scale converge to some function u0, which is a function of 2 variables, the macroscopic variable x and the small scale variable y. And it satisfies the following limit equation, which is already looking a lot better. Now we have derivatives with respect to y being captured here. But if anybody's interested, this still isn't enough to capture the spectrum in the whole space. But that's a story for another day. And I definitely won't be talking about that today. But we have the following 2-scale homogenization theory that says that these operators A epsilon are strongly 2-scale resolvent converging to an operator A0. It's like this. And this notion was introduced by Vasily Zhikov in his work in 2000. And along with this came a statement in the paper saying that if an operator strongly 2-scale resolvent converges, then you have Lowy semi-continuity of the spectrum in the following sense. Every point in the spectrum of the limit operator that you arrive at will be a limit point for a sequence of points in the original spectrum. And for the first half of the story, the remaining question is, what about the reverse inclusion? Have we captured the entire limits in spectrum? And the reason why I arrived at these problems, well, the reason why I became very interested in these problems, not why I arrived at them, but is because even for this 2-scale convergence, for degenerate problems, this is not true in general. So there is some work to be done. And I wanted to understand why this is
I'm not
true.
familiar with all this. When you say there exists lambda epsilon, you mean there exists the sequence epsilon n tending to 0.
I mean, for every epsilon, you have an element of the spectrum A epsilon. This forms a sequence.
For all epsilon or
For
you
all
need a
epsilon.
subsequence?
No, for all epsilon. If the sequence A epsilon converges to A naught, then you can construct a sequence lambda epsilon converging to lambda naught.
Yeah, it means that it's a sequence.
It's a sequence. It's a consequence of the convergence, just like the normal resolvent. If you have no strong resolvent convergence in the normal topology, this is true. This is just the analogous with the weak topology. Weak convergence, I shouldn't say weak topology. So the converse statement, is it true? Well, in the high contrast case, the work of Vasilichikov again in 2000 in the bounded domain, and in 2005 in the whole space, he works on this problem. So we're just in the high contrast problem again, we're looking at our original problem. And we have some f epsilon that come too strong with 2-scale converges to some f. Then we know up to a subsequence this time that u epsilon strongly 2-scale converges to a function u naught, which is a function of 2 variables. And this function is u of x, which is independent of the microscale, plus v of xy, which is supported on the pole. And it satisfies the 2-scale resolvent limit equation, which is this equation here. And I wrote it here because this equation in one form or another will start appearing again in the work that me and Kirill did later on. But what's interesting here is it's an equation of 2 variables, x, the macroscopic variable in the whole domain, and y, the variable on the periodic cell. And it's coupled, you see here. These brackets here mean the mean value of v with respect to y.
Can I just ask the question again? Is there some natural nesting of your sequences? Do you need it only to find for a subsequence of epsilon?
Yes,
Or for every epsilon?
and this is a subsequence here.
You just need to, once you have a subsequence, it's fine.
Once you have the subsequence, then you can apply the previous statement for this subsequence, and it's fine. So, this is a strong 2-scale resolving convergence, so this is ensured. And the reverse inclusion was shown by Jacob in this work, that if the matrix Q1, if you remember this is Q1 now, the outside of the ball in the periodic cell, if it's connected, then the reverse inclusion holds. And this is why I put dimension greater than or equal to 2 here, because in dimension 1 this set is never connected. And you have the following reverse statement. So the limit of the spectrum of the set of spectra is sigma A naught. So I was gonna, okay, but we'll see how it goes. So so now we know that what the limiting spectrum is, what does it look like? So I'm in the whole space now, and I want to know what the spectrum of sigma A naught is.
By limit, you mean all the accumulation point
Of this set. I mean in the sense of what I wrote here, Hausdorff convergence. Too long ago. I mean here, in this sense. That's what the symbol means for me. Every point of the set S, lim. So sigma n naught.
There exists a sequence of epsilon n.
This is what it
Not
means.
subsequence.
What it means is this picture here. What it means is this.
There exists some subsequence epsilon n tending to 0, that's that?
No.
all
sequences.
sequences,
The whole
epsilon
sequence.
There is a family.
If it's a subsequence, then just call your whole sequence the subsequence. It's for the sequence. If I write this, I mean this. I mean it for the whole sequence. If I write this, then I mean it for a subsequence.
Okay.
So it's for the whole sequence. I thought you had some natural nesting.
If I establish this statement for some sequence epsilon, then that's what it means.
Okay.
Sorry. So anyway, so now I've got the operator A epsilon A naught, looks like this. I want to know what this spectrum looks like in the whole space case. Because we're interested in the whole space and parts to begin with. So let me formulate the eigenvalue problem. So Aom is an elliptic operator. Elliptic matrix is positive, constant coefficient matrix, it's elliptic. And we have this spectral problem, but it's coupled, you see? In the equation supported on the inclusion, you have u of x, and in the equation supported in R, for x in R, sorry, this is y in Q2, x in R, sorry. You have the mean value of v. But if you look at this second equation, it's linear in x. So you can write our solution v as lambda ub, where v just solves this Dirichlet problem on the inclusion, with the Dirichlet-Laplacian problem on the inclusion. So if you perform a spectral decomposition for this v, then you arrive at the famous equation for this limiting spectrum. And what you have is you have a spectral problem, say in the x in the whole space here, but the spectral parameter, the right hand side is nonlinear in the spectral parameter. And this beta is written in terms of the eigenvalues and eigenfunctions of the Dirichlet-Laplacian restricted to the inclusion. And it has the following picture, where these asymptotes are the eigenvalues of the Dirichlet-Laplacian on the inclusion, whose eigenfunctions don't have mean value 0. And because this is a positive, because it's an elliptic constant, and the spectrum of this operator in the whole space is the positive real axis. So the beta of lambda such that this is satisfied, or where beta of lambda is non-negative. So this gives you the absolutely, it's really wonderful. I mean, you've got here you've got the band structure of the limit spectrum in terms of this beta. And you know where its beta is non-negative. And you also have the spectral convergence statement. So for small enough epsilon, you know that your operator A epsilon band structure, absolutely continuous spectrum will look like this.
Sorry, this beta looks like, this sum looks like coming from perturbation theory, does it? Or, this is normal?
Spectral decomposition.
Spectral decomposition.
So it's simple spectral decomposition.
Spectral decomposition.
It's not perturbation, it's just exact.
It comes from the fact that you've captured the coupling between the two scales.
Okay.
And when you put the mean value of v here, you just get the mean value of b. And then you end up with this term.
Okay.
But it seems like you always have infinitely many gaps.
Yes, for this limit spectrum, there are infinitely many gaps.
Yes.
That's a fact.
The limit behavior breaks Bethe Sommerfeld conjecture.
It does, yes.
But
for small epsilon, the original spectrum is only close to this. So it doesn't contradict
The
anything.
number of gaps will go to infinity, right? But
And it leads you to the interesting question, how fast does this spectrum converge? The original spectrum, how fast does it converge to the spectrum given by this beta? And that's the second part of the talk that I hope I will get to before today. I will provide the rates of convergence before the end of this talk, I hope. Anyway, there's one little bit left here. This limit spectrum isn't just absolutely continuous, it also has eigenvalues, with eigenfunctions of infinite multiplicity. And they are, well, let's look at the eigenvalue problem again. And now, let me have an eigenvalue with the Dirichlet-Laplacian on the inclusion that has an eigenfunction with mean value 0. I will take this phi and set it to v, and I will set u to be identically 0. So the top equation is satisfied, 0 equals 0 plus 0. And the second equation is just the eigen, because u is 0, this is just the eigenvalue problem for the Dirichlet-Laplacian on the inclusion. So there are eigenfunctions here as well, and they may be anywhere in this picture. Right, so we know what the limit spectrum looks like, but I want to know how fast it converges. We know in the classical case we have the results of Bim and Susskind that tells us that the resolvents between the two problems are epsilon close. But you can't get a result like that here. What you can say is if you have a solution to your original problem u epsilon, and you have a solution to your limit problem u naught, well u epsilon depends on x, and u naught depends on x and y. It's a function of two variables. So the best you can say is u epsilon minus u naught x over epsilon, where you replace y by x plus the ratio of scales. And that's what you can say. It will converge to 0 as epsilon goes to 0 in the L2 sense. But you can't, we want some non-resolvent statements. And in general, you can't bound this by the norm of f epsilon on the right hand side plus some constant. And the difficulty is that these resolvents are defined in different spaces. So the traditional notion of non-resolvent convergence is not applicable here. So So what did we do? So the challenge, what the goal for us was to, I've called it A on epsilon. I can call it whatever I want, right? If you introduce it, you can give it a name. So I call it A on epsilon. And I want to find some operator such that its resolvent is asymptotically close in the norm, to the original problem. And actually, not just asymptotically close, but bounded by C times epsilon. Every time I've shown this to people, somebody has always said, why don't you just set A on epsilon to be equal to A epsilon? But the point here, the point here is A on epsilon is supposed to be the leading order term in the asymptotics of A epsilon. It's supposed to give us the simplest characterization of the behavior of this operator with respect to epsilon.
Operator with constant coefficients. An operator with constant coefficients.
High contrast problem. The high contrast problem. With the constant coefficients, I just set this to be the classical homogeneous limits.
No, the structure of A home superscript epsilon.
Yeah.
Almost constant coefficients.
It's almost.
He's asking, will it have constant coefficients?
Oh, it's more difficult than this. It's well, the operators will have constant coefficients, but I will describe it in terms of some kind of flocky block decomposition. So I will have a family of operators with constant coefficients, but where I define them will depend on epsilon. I have 30 minutes.
I think the point is that this operator is much simpler than A epsilon.
It's a lot simpler than A epsilon. It's the simplest you can get in the sense that from this A on epsilon, I will be able to determine information about the spectrum. Useful information. It's simpler, that's the point. If you want to think about it, it's the leading, it will perform some kind of asymptotic expansion in the operator sense on this operator, and it's the leading order term in the asymptotics of this operator.
But is there any sense, any moral sense in which we can think of this as operator almost with constant coefficients, or is it?
Yes.
Yes.
Yes, you will.
Okay.
Yes. Soon you will see, hopefully.
Okay.
So this is the goal. Okay, so the introduction to homogenization is over, and now I will begin my talk. 25 minutes. Okay. So. Right, we won't be using homogenization theory. Now we're going to jump straight into flocky block theory. So now you will all be a lot more comfortable, hopefully. So I have a problem with periodic coefficients, and you know that this problem on the whole space, you can relate it to a family of block problems. The only thing I want to say to you all here is I will look at my problems on the periodic cell. I will keep the theta dependence inside the definition of the operator. I won't in the following sense, in the boundary conditions. I will be looking at quasi-periodic solutions. I won't put them inside. I won't write grad plus I e theta, for example, I theta. And we have the Gelfand transform that tells us that this operator is unitary equivalent to this fiber decomposition. Now the interesting thing here is we have a family of operators that depend on the parameter epsilon. So we have in some sense this kind of flocky block decomposition. And I want to find the asymptotics of these operators in epsilon. But these asymptotics have to be uniform in theta, otherwise you gain nothing. Because you just like want to integrate into traditional sense if you wish. So it needs to be, these asymptotics of B epsilon theta need to be uniform in theta.
There's a subtle issue you have been hiding, that the period also depends on epsilon, right? And this should...
Everybody asks a question one slide before this slide. Yes.
I mean,
but it's not so right. So basically, I'm looking at L2 norms, okay? So if you do a change of variables, you can make the change of variables operator, you can scale it so that it's a unitary mapping L2. So let's just rescale the problem so we no longer have a problem with period epsilon, and now we just have a problem with period 1. So now we'll have epsilon 1 over epsilon. So the coefficients are now blowing up in the matrix and order 1 in the inclusion.
so on the previous slide, should have put epsilon, more of epsilon, right? Like the brilliant zone depends on epsilon, right? It's not
No,
zero
for a
to,
coefficient B, the
it's
brilliant
not,
zone.
it's not 0 to 2 pi, right?
Here?
The old cell size, generally, right?
Well, I mean,
Before
this
you-
is.
before-
I haven't said
before you
anything
start
wrong here
scaling.
because the B I wrote here, I assume still has period 1. So the dual cell will not change.
Okay, epsilon is just the amplitude.
Yeah.
So yeah, if I'd done a flocky block decomposition on this problem, then I would have to put a parameter in here, and the dual cell will be growing. But well, you can do this too, but I prefer this way. I prefer to keep the Joule cell fixed. So that's why I will do a change of variables, and it changes nothing when you look in the L2 norms. So now let's think about this picture now. Coefficients with period 1 and 1 over epsilon squared in the matrix and 1 in the inclusion. And I want to look at the asymptotics of these block fiber problems with quasi-periodic boundary condition. So here I've written now that my function is in H1, W12 on the cell Q, and this subscript theta means it has quasi-periodic boundary conditions. Well, actually, the asymptotics for these for fixed theta are quite simple. So let's go through it. We can look at it in our multi-scale expansions. So let's seek an expansion U0 plus epsilon squared U1. You can do it for all terms actually, but I'll only just look at the first term. So at order epsilon minus 2, you get this identity, which tells you that U0 is in a space I will call V theta now, which is a closed subset of H1 theta, characterized by the fact that the gradients are 0 on the matrix. And then you look at the next order term in the asymptotics, once you plug this asymptotic expansion into the equations, and you get this following equation. And I'll explain on the next slide to preempt any questions. The solvability condition for this equation is if the right-hand side is orthogonal to any function in V theta.
Maybe for this audience in Marikel, perhaps was commenting that for after you've done this rescaling period is 1, epsilon minus 2, it's only if you denote it by lambda and lambda goes to infinity, this becomes identical to large coupling limit.
Yes.
Hempel-Lee analysis.
Yeah, it's written. It will in time.
Right.
Your impatience.
What is Chi1?
Ah, good question. Chi1 is the characteristic function of this set without the ball. So it's a degenerate PDE. So it has this operator has a non-trivial kernel.
Chi2 is the 1 minus, and Chi2 is.
And Chi2 will be inside, but we won't think about Chi2. So I just need here. Oh, we have Chi2. Sorry, Chi2 is inside. So yes, you're right. So I just want to
just a quick question. The condition that you had, Zhigor's condition that Q2 has to be connected.
Q1.
So this
Q1 has to be connected.
Q1, it's
okay.
it's complement to Q2.
Yes,
Okay.
Q1 has to be connected, and it's so that you can get kind of Poincare type statements. The solvability statement.
Q2 it can be.
Yeah.
You can take 5 balls.
Yeah, Q1 is the connected one. So the solvability condition tells me here this: we have a solution U0 which lives in V theta and it satisfies this variational form of V theta. So let's have a look at this a little bit more. Well, when theta is not equal to 0, V theta is nothing more than just H10 supported on Q2. Because we need a function that is constant in Q1 but satisfies quasi-periodic boundary conditions. So it's just a 0 function outside the ball. And then the form just becomes the Dirichlet-Laplacian on the inclusion, the resolvent of the Dirichlet-Laplacian on the inclusion. So we have something quite degenerate here. For all theta in the Joule space not equal to 0, all of the operators pointwise converge to this operator. And for theta equals 0, well, again, this condition tells us that the function is constant in the matrix Q1, but the periodicity condition doesn't kill this constant. So our function can be written as a constant plus a function supported to the inclusion. And we have the following variational form here. And you can write this in strong form if you want to, but it's going to be the last time you see it on this slide, so I won't bother. And what we do have is what Valery was saying, is that there is a work of Hempel and Leonau in 2000 that actually says that these two problems, in the limits bound, strictly bound the spectral bounds of the limiting problem. And you actually saw this from the problem, from the Jikov's work. Because we have this function, the eigenvalues of these two problems, sorry. Because we had this beta, we had this function saying that the first eigenvalue of the inclusion. And we had this function saying that when beta was non-negative, then it was in the limit spectrum. Well, these are exactly the eigenvalues of theta not equal, the limit problem for theta not equal to 0. And for when theta equals to 0, its spectrum is characterized by beta's lambda equals 0, in fact. So these two problems the spectra of these two problems bound the spectrum of the limit, the spectral bands of the limit. Ignoring the eigenvalues where all of its mean values are 0, because then they won't be in this picture. So, well, these pointwise problems are certainly not suitable, right? We have an operator that's has an absolutely continuous spectrum, and in the limits we just have two operators with discrete spectrum. So we can't capture all the spectral information from these pointwise limits in the block space in theta. And why is this? Well, I'm going to look at the solvability. I'm going to look at the inverse operators for these problems that allow me to determine the asymptotics. And you can look at this by using solvability condition. How did I know that this problem had a solution? Well, I used this more general result, very earlier here, that they were developing during my PhD, in fact. And it says if you have, in this specific setting, if you have a force in the dual space of H1, such that it's orthogonal on the space V theta, which is the kernel of this operator, then there will be a solution as long as this Poincare type statement holds. And here, this is the projection on the orthogonal complements of V and the H1 norm. And you have, and it says that the H1 norm of this projection is bounded by some constants times the gradient of the function just supported to the Q1 phase, Q1 outside the ball. Without going into the specifics of this, you can show that this is true, but what's important to capture this degeneracy is we want to know how this C behaves with respect to theta. And that's the first result. It's the function looks like this. So it's just a constant at theta equals 0, but if you come to the 0 in the box space, if you approach 0, this constant blows up by 1 over theta, absolute value of theta. This allows me to get error estimates between the difference between u epsilon and u0, for theta not equal to 0. And we have these following resolvent estimates. So the resolvent of the fiber b epsilon theta and this limit operator, the pointwise limit operator, is bounded by epsilon squared over theta squared. So if anybody here are familiar experts with singular perturbations and boundary value problems in the physical space, you have an asymptotics which holds in the bulk, but this asymptotic starts to become invalid as you approach the boundary. And there is a small layer around the boundary called the boundary layer where a different type of asymptotics must hold. You have exactly this type of phenomena happening here, but not in the physical space. Now it's in the floppy block joule space. And that's the observation. There's a boundary layer here in the neighborhood of theta equals 0. These asymptotics are no good. Once you go no good for order epsilon. And in fact, the closer you get to theta equals 0, the worse this error bound becomes. So you want to do something different. While keeping with the same analogy of the boundary layer, you just perform a stretching change of variables with inside theta, inside this annulus. So I will write theta equals epsilon theta 1. And now I don't want to work on the problem. Now because my quasi-momenta depends on epsilon, I don't want to work on b epsilon theta, where theta is in the boundary conditions. So I'll just do this change to push myself onto problems that are periodic on the boundary of the Q, and you put the epsilon 1 theta 1 now inside the operator, and inside the derivative, the differential form. And if I do some asymptotic, this is a bit more complicated than the last asymptotics. But if I do this asymptotics, then you end up with a limit equation. And this, well, everybody, apart from the people who know this work really well, this might start making you think about the two-scale limit operator. And actually, if I take the two-scale limit operator, what you had here is you had div x grad x. And if I perform the Fourier transform in x, you would exactly get this equation where c was the Fourier transform of u, and now my Fourier variable is theta 1. But theta 1 now is inside the ball. Well, theta is in a ball of radius square root of epsilon. And theta equals epsilon theta 1. So we have, so theta 1 is in an expanding ball of radius 1 over square root of epsilon. So as you go, as theta epsilon goes to 0, this theta 1 is taking more and more values in the whole space, and this is becoming more and more like the two-scale limits operator after a Fourier transform in the first variable. So we have some parallels up here. But the story isn't finished, unfortunately. Again, people who are familiar with multi-scale matched asymptotic expansions, you have an outer expansion that is well behaved away from the boundary layer. As you approach the boundary layer, it blows up. But if you have an expansion inside the boundary layer, once you leave the boundary layer, it blows up. So we have to handle this problem. And in fact, it says that the difference between our solution for the fiber, the non-resolvent error estimate between the fiber b theta epsilon and this limit is bounded by a theta. So we only get all the epsilon error estimates if we're in the ball of radius epsilon. So one more picture. So we have the dual space. And we have, okay, I put theta equals 0 in the picture. Let's put theta here in the maths, but in the picture theta equals 0 is here. And this is a ball of radius square root of epsilon. And we know here that we have the outer expansion, and it gives all the uniform in theta or the epsilon error estimates. And now we just ball of radius epsilon here, we just found the inner expansion, which gives uniform in theta or the epsilon error estimates. But then we have this annuli region, where once we start to come into the annulus from the outer expansion or into the annulus from the inner expansion, the error estimate starts to decrease. So we have a partial result.
Standard terminology is inner domain, outer domain, and overlapping matching.
Matching region.
Keep that
Yeah.
dimension, right?
Okay, from the in analogy to the physical space. Yeah. But now we're in the spectral space.
Yes, as you said.
So we have these operators and we have these error estimates. That's what I just said. We have the fiber b epsilon theta, and we know that it's uniformly close to the outer problem here and uniformly close to the inner problem inside here. And I've got some projections here because, well, these are you're projecting the force with respect to this subspace, but it's not so important for what I'm saying. So once you go inside this annular region, the matching region, the estimates start to worsen. But we have this partial result that says, well, if I don't want to lift this up again because it's a pen, but if I chose a ball of radius epsilon to the power alpha for some alpha in this region, and I'm gonna go up. So I have a different look. So if I chose a ball of radius epsilon to the power alpha, so this is epsilon to the alpha, and I made my outer expansion come in to here, and my inner expansion come to here. Then we get there in an error estimate. It's not the best, but it's a good one. And it's of this form. We have so now I've taken over, so that's what this fiber decomposition is telling me, what I just said in words, and I take the Gelfand transform, and I get that this is uniformly bounded by epsilon to the power alpha plus this. And this error estimate is maximized if I chose the ball to be of radius epsilon to the power 2/3. And so you get a 2/3 on the right hand side. It's not epsilon, but it's 2/3. But we know we have the analogy with the matched asymptotics in the physical space. So we should try and match in the spectral space. And if you do this, we arrive at something called a matching operator after a little bit of work. And it looks like this. It's very similar to our inner problem if theta is epsilon theta 1, because this is small, and you have the theta 1 dot theta 1 term. And it's similar to our outer problem if you are outside the ball of radius epsilon to the square root. And then we have the following main result. This matching operator is uniform in theta, epsilon close to our fibers. That's the first result. So if I perform a Gelfand transform, it's uniformly close to the b epsilon. This is the one with the period 1 and coefficients 1 over epsilon squared in Q1. So then I perform a change of variables, y equals x over epsilon, and I arrive at the original high contrast problem. And this is the leading order asymptotics, where b0 epsilon home is now this one, what I've called here the matching operator. And well, the matching operator is a good word, because well, if we go inside the ball of radius square root of, outside the ball of radius square root of epsilon, it's epsilon course uniformly fitted to the outer operator. So that's good. And if I go inside the bow of radius epsilon, it's uniformly cosine theta to the inner operator. So I feel like it's a good way for the matching operator. So now we have error estimates, non-resolvent error estimates between A epsilon and this term. So all that remains to do is now study the spectrum of this operator, A epsilon home. I mean, we want to, well, is the spectrum simple, or have we just gone in a big circle? Well, outside the bow of square root of epsilon, we know that it's close to B0.
Tau, what is big tau?
This is just change of variables, y equals x over epsilon. That's been normalized so that it's a unitary operator, not two. So I think maybe 1 over square root of epsilon. Well, no, d over 2.
Projection or something, right? Yeah.
The projection, yeah, there were, again, it's because our limits operators were defined on closed subspaces about 2. So you have to project the force into. But what's important is this object here. And there should be an epsilon here, sorry, it should be b on 0 epsilon, not b on 0. Means nothing. It should be this term here. So outside the bow of radius square root epsilon, we know that it's uniformly close with respect to epsilon. Epsilon uniformly close in theta to b0, and b0 is just the division of the Laplacian on the inclusion. So if you think about the picture, you're in the Flocky box space, and you go out for a fixed epsilon, and you go outside the bow of radius square root of epsilon. The rest of the entire Flocky box dual space is only contributing to this part of the limit spectrum. An enormous part of the dual space, it contributes to a very small part of the spectrum. It's just the left-hand part of the bands and the eigenvalues of infinite multiplicity. And then the rest of the spectrum is coming from this very small region, square root of epsilon. So in the region of square root of epsilon, we have this is the eigenvalue problem. I should have brought this up. I'm sorry. So we have this operator b on 0 epsilon, and this is so if you wish formally, well, this is the spectral problem. And I'm going to do a change of variables first, and why theta 1 equals theta over epsilon. So now theta 1 is like I wrote here. It's in a bowl that's expanding at the rate 1 over square root epsilon. And this problem just simply looks like this. And now, as in with the Jirkov high contrast, as in with the Jirkov two-scale limit, I will perform a spectral decomposition on this these two equations here, which is just a problem restricted to Q2. So now that we have a decomposition with these epsilon appearing here, where we have whereas before these are the eigenvalues, lambda k are the eigenvalues, and phi k are the eigenfunctions of the division of Laplacian restricted to the inclusion. And you end up with this following spectral problem. It looks a little bit like the Jirkov one, but now we have beta that depends on epsilon in this simple way, and we have theta 1, which is now in a bowl with radius 1 over square root epsilon. It's not quite the whole space. But as epsilon goes to 0, beta epsilon just converges to beta. And because A home is an elliptic, the left-hand side, the image of this just converges to the whole space. And you have that the limit of this spectrum converges to where beta of lambda is non-negative. And beta is Jirkov's beta function. So that's all I wanted to say. Thank you.
Absolute value for this, for complexities, right? You don't take square over complexity.
Yes. It should be there should be a bar.
A bar over, and therefore below you have not round brackets but straight brackets, right? In the last formula.
At some point I did do a course in complex analysis, I think. Yeah. Thanks for reminding me.
Questions? Yes.
So there was the question in the beginning, what happens with this when you have the Laplacian plus potential?
Well,
you said it's sort of, it's
if the
potential, the same results hold, or?
For classical homogenization, it is trivial before you start introducing high contrast.
Yeah, and high contrast.
Just averaging, right, in contrast to the cell problem solution, which is but for no one really looked into
No.
if you introduce actually for Maxwell's there is some duality, right? You can if you reduce the first order Maxwell system one way or other, right? In
Yeah.
one way you have high contrast in epsilon, in
Yeah.
other way you have
Contrast in mu.
no, not in mu, but
the
in
density.
1 over epsilon in the potential like
Yeah. Yeah.
and they must be identical in the end, right?
But the high contrast in epsilon term has been, this was a work done by me and Kirill, who will be talking about it in a few weeks, but in the density term, it's open.
In fact, we tried with Ilya and our then postdoc Natalia Babic a few years ago
Oh, yeah.
to inject a bit of contrast in
Yeah.
this. No, not exactly potential in density. You know,
Density.
if you introduce for spectral problem, right? You have a left hand side and you have a right hand side, and on the right hand side you L2 lambda times u, right? But you write lambda rho u, right? And rho depends on epsilon, right?
But this is-
No, I wanted to know,
Limitation.
okay, that's one thing. No, my question is, say, plus 1 over epsilon squared potential. Laplacian plus 1 over epsilon squared potential.
Well, I mean,
Is this done or not?
It's
no,
not
it's
done.
different.
it's,
Semiclassics and homogeneous.
No. Potential exactly
PV
like
term.
x over epsilon.
To
take this operator plus
essentially.
epsilon square
Okay.
We are not sure.
times periodic potential.
now, these are Schrodinger, we don't work with the Schrodinger problems, but the underlying mechanism. you
But
should
it's
be-
almost the same. I
It's
mean,
almost,
if you,
well, they're almost the same is by problem formulation. If you can formulate your potential problem into such a way that when you get a floppy block decomposition, you get something that looks like this. But it's not the same because in this case the contrast is in the coefficients epsilon squared, and you have two derivatives which give you a leading order term. If you put 1 over epsilon squared in front of your potential, you're going to have the potential appearing in the epsilon minus 2 of the asymptotics. It's not appearing as leading order. And I'm not so sure how to proceed.
no, but then you put the 1 over epsilon squared in front, yes?
This is
Make a high
1
contrast.
over epsilon squared.
I
If you
see.
put the 1 over epsilon squared in front, then the potential appears in the first order term of the asymptotics, which is order epsilon minus 2. It's a singular expansion.
Sorry, so I'm also interested in this. So what is bottom line about just the potential? So when we just have Laplace plus potential and then try to rescale, I mean, introduce epsilon
Which is the
somewhere
potential. And
with
it's
just
just
the
all of
potential.
pretty
So
simple
what,
fashion.
I mean, is it not what people have been doing in homogenization? This is what you are saying. I mean, just general question.
No, so some people have been doing this stuff as
Yeah.
well.
And so these are questions that make sense but have different answers. This is what.
A bit different answers, but mostly they were not looking at it in the case when you have high contrast. So what you're saying, epsilon to the power minus 2 potential, it corresponds, roughly speaking, to classical homogenization.
And what do you mean by classical
By classical
homogenization?
homogenization, it is without degeneracy.
Okay. So let's talk about classical, yeah. So let's say that we have no degeneracy. So then people were doing this.
You should be able to just turn the handle on such a problem.
Well, because my next question is going to be given the overall large theme of the program. Have been people doing the same with quasi-periodic potentials?
No.
It's completely different ballgame.
Well, I do understand, yes, but I mean, so is it completely open season? I mean, nobody knows anything?
Random potentials. People consider it as a case of random. Random.
Yeah, but quasi-periodic, the answer is no, yes?
No.
At the level of formal asymptotics, you can do some repeat this calculation, and you can end up with something resembling, in some respects, Anderson localization. For example, in the sense that, suppose, like, a chain had a periodic, nice round circles, same size, right? But suppose, like my naive understanding of this almost quasi-periodic things, you imagine three-dimensional balls, right? Three-dimensional identical balls, periodic, and then you cut them by a plane with irrational parameters. On a cross-section, you will have kind of distribution, quasi-periodic distribution of sizes, right? And as a result, each inclusion has set of eigenfrequencies, right? Where something happens, this funny function beta blows up. But now these sets are changing.
Well, I
From ball to
don't
ball?
have balls. I have potential. I have potential. Then I
Right.
will scale it. But my potential is quasi-periodic to begin with.
I see.
Does it make any sense? And have been people
Without high contrast, I think it sort of embeds into some generalization of a non-periodic homogenization, generalizations to quasi-periodic, almost periodic coefficients, ergodic algebras, goodness knows what that's. Then
So
the
there are
answers-
results
the answers are still classical, right? Then the limit equation has constant coefficients, right?
There are papers.
Yes, and averaging for the potential with respect to periodic.
The point in this game is that introduce the degeneracy to get non-classical.
Yeah, I understand it's completely different ballgame. Yeah, it's but I just want to introduce a little bit of quasi-periodicity, as I said, given the overall subject of the program. So what we are saying is that you can generalize it sometimes to quasi-periodic, almost periodic, even if dimension is higher than 1. Yes.
I don't know. You can play formal asymptotics game, but I personally don't know how to prove anything. Maybe
Okay, so you can
maybe
get
because
some
of my sort of embarrassingly low level of sort of technical knowledge of.
No, but that's
almost
fine. The
classic.
question is, does it exist in the literature?
What?
Has anybody looked at classical
Roman.
homogenization in the case of quasi-periodic
Yes,
potential?
of course. Classical, that's all.
So maybe that's what we should learn, and then one can ask, is there other questions
Right.
like this one, or high contrast with potential, where you don't know the answer?
But what we are saying, I mean, so if we have this classical homogenization for quasi-periodic potential, so you are saying that people know the answer but cannot prove it. Is this what you are saying?
For high contrast.
For
Yes. High
yes.
contrast, you can derive some intriguing looking answers, right? But question is maybe the rest of the what this program is for, right?
Because maybe we could arrange some group of people who are interested in this and have a further look at it. Okay, let's talk maybe in sort of smaller company. Let's discuss it further. Further questions? Marcella?
So at a certain point, I remember there was a condition on Q1 being connected or something. So does it mean that if your ball is bigger than the square and then you disconnect this pieces without epsilon square, something change?
Well, it can't be bigger than the square because it wouldn't be a periodic reference.
No, you can't.
Yeah, so things will certainly change. I did a paper with Kirill in 1 dimension where it's always disconnected, and the spectra, the answer is totally different. Everything changes.
So if you put
But
epsilon
this
square
framework can
outside
still be
and
used.
one inside the ball, it's...
Yes, if you put epsilon squared outside and 1 inside for this problem, you would, if you look at the literature before and now, you would not know what to do, but if you do what I did in the second part of the talk, you get the answer. And in fact, you end up with a family of floppy block limits operators. So theta equals 0 is very special here, but if you switch it, not all theta are equally important. There is no special theta. So the theta equals 0 corresponds to periodicity. So the small scale behavior in the 2-scale convergence says that the periodic small scale is important. But when you switch the coefficients like this, the all quasi-periodic behavior on the small scale is important. So if you did 2-scale convergence, you wouldn't get an answer that would give you the spectral convergence. You would miss parts of the spectrum.
Other questions? Okay, let us thank the speaker again. So next week we will, so next week we are planning 2 talks. And first of these 2 talks will be on Tuesday by Kostya Hanin. And it will be the talk that will sort of try somehow to merge our program with the dual program on random geometry. So we will try to, actually he promised he would give a talk that would be interesting for both programs, and then maybe we could have some discussion and involve people from the other program as well. And that's why I am aiming to have this Kostya's talk in big room, in seminar room 1 rather than here. Okay, so that's the idea. The second one will be on Thursday, and it will be one distillation.
Информация о спектре теряется.